we had introduced ourselves to the concept of Laplace transformation of a function of time in the last class, and we had a look at the Laplace transforms of some important functions of time like the unit impulse function, the unit step function, and the two sinusoidal functions cos omega naught t and sin omega naught t. Let us first recapitulate some of the important points that were discussed in the last class. We are concerned with functions of time which are causal. So, the f of t which we are concerned with are causal, that is f of t is 0 for t less than 0, and further we said they are of exponential order. That means limit as t goes to infinity of f of t e to the power of minus st goes to 0 for real part of s greater than some number sigma c for some sigma c which is a function of f of t. So, if the function of time is of an exponential order, that is as t goes to infinity, this e to the power of minus st is able to pull this down to negligible proportions, then for such some time functions we said we have a Laplace transformation f of s which is given by the integral from 0 minus to infinity of f of t e to the power of minus st dt, that is the forward Laplace transformation formula, and the inverse Laplace transform is given by 1 over f t is 1 over 2 pi j c minus j infinity to c plus j infinity of f of s e to the power of st ds. This is the inverse Laplace transformation formula, and this contour of integration which extends from c minus j infinity to c plus j infinity is a vertical line in the region of convergence of the Laplace transformation. That means c must be larger than sigma c, and this contour of integration, as I mentioned, is referred to as the Bromwich contour. Now, as a result of this, the Laplace transformation that we get is usually a rational function for the type of functions of time that we consider. So, for the given f of t that we are having, we have an f of s which is a rational function, and this rational function, by rational function we mean the ratio of two polynomials in S, and this could be, the two polynomials could be put in the form m if the numerator is factorized as s minus z1, s minus z2 down the line to s minus zm, and the denominator likewise is factorized as s minus p1, s minus p2, s minus pn. Then the Laplace transformation f of s is defined by the values of the z values z1, z2, z3, zm, and the values p1 to up to pn apart from the constant multiplying factor m. So, this f of s can be represented in the complex plane by the location of the zeros of f of s and the poles of f of s. So, zeros are normally marked by means of small circles. So, these may be 0 locations. Poles may be are marked by a crosses. So, there may be a pole here, a pair of poles here, etc. So, the pole and 0 locations are marked in the S plane So the pole and 0 locations of f of s completely define f of s except for the multiplying factor m. And we also note that as long as the coefficients in the two polynomials are real, then any complex pole is accompanied by its conjugate, any complex 0 is accompanied by its conjugate. And the abscissa of convergence is sigma c, the abscissa of convergence is larger than the maximum value of the real part of pi. So whatever the pi you are having is the maximum value of the real part of pi I from 1 to n. So that will be define the abscissa of convergence. That means the region of convergence starts from the rightmost pole. So if this is the rightmost pole, anything beyond that is the region of convergence. So the maximum value of the real part of the poles defines the region of convergence. And we have seen this in the case of simple functions like the unit step function, which has where sigma c is 0, the e to the power of minus 2t where sigma c is minus 2, and so on and so forth. That is what we have seen earlier. A few comments about the notation. As I mentioned, the Laplace transform exists for unilateral Laplace transform that we are talking about, exists only for causal time functions. So if f of t by definition has a value for negative values of time as well, to make sure that we are talking about the truncated part of that function of t, we normally write f of t ut, to make sure that f of t, the composite function, is 0 for negative values of time. Often instead of f of t ut, we use simply f of t when there is no cause for confusion, when there is no room for confusion. In other words, example, suppose e to the power of minus 2t, this is f of t, but we can't find the Laplace transform of such a function. We have to find the Laplace transform of e to the power of minus 2t times ut. So when you have got 1 over s plus 2, the inverse Laplace transform of that is e to the power of minus dt ut. Instead of that, we write e to the power of minus 2t itself, with the understanding that we are talking about e to the power of minus 2t valid for t greater than or equal to 0. So as long as we have understanding that whatever time function we are having is valid only for t greater than or equal to 0, and it is 0 for negative values of time, instead of e to the power of minus tt ut, we often write e to the power of minus 2t to save our writing. Another point is, suppose we have a constant Laplace transform of some constant k. Again, by definition, a constant k exists for all time values of time, but in the context of Laplace transform, we assume that this function is a value k starting from t equals 0 minus, because we can treat only functions which are 0 for negative values of time in the Laplace transformation consideration. Therefore, even if you want to find the Laplace transform of a constant, we regard that constant, that we have that function to have a value k starting from t equals 0 minus and 0 for values of t less than this. So when we are talking about a Laplace transform of a constant, we treat this as Laplace transform of k ut and say this is k upon s. So we do not sometimes exhibit specifically this u of t, it is understood, just to say or write it. Another feature of the common notation is, you recall that I said cos omega naught t ut has Laplace transformation s over s squared plus omega naught squared. we have taken a particular angular frequency omega naught and truncated it at t equals for negative values of time and arrived at this Laplace transformation. Now S is equal to sigma plus j omega. The imaginary part of S is also given the symbol omega, it is a running variable. And to distinguish that running variable omega with this omega, so we have given a special symbol omega naught. But in our manipulation we very rarely decompose S as sigma plus j omega and look at the imaginary part of S. So where there is no confusion, we even write simply cos omega t having a Laplace transform as S squared plus omega squared. Often this is written in this manner. In this notation we understand that this omega is not to be confused with the imaginary part of this S. This is omega is a particular value of omega associated with the trigonometric function. This should not be confused with the imaginary component of S. And secondly, as we mentioned earlier, actually we are talking about cos omega t ut, but this additional function u of t is often dropped, assuming that we are talking about functions which has this functional notation only for t equals 0 plus onwards, 0 minus onwards. So often instead of writing like this, we simply say cos omega t as the Laplace transform S over S squared plus omega squared. These are minor deviations in the notation we often find to simplify the writing out the various expressions. This type of simplification is resorted to. But basically we must note that whatever function we are talking about is assumed to be 0 for values of t less than 0 minus.